So first of all, I would like to thank Dhiraj for accepting our invitation. It's a pleasure to have him here at the CosmoVerse seminars. And Dhiraj is currently a faculty at the Institute of Mathematical Science at Chennai in India. Prior to this, he earned his PhD from the Harish Chandra Research Institute, and then he joined the Asia Pacific Center for Theoretical Physics in Korea as a postdoc. Then he moved to the Laboratoire APC, Université of Paris Diderot in France, then to Bologna, first as a INFN fellow, and then like a INAF fellow as a Marie Curie Astrophit. So his main interests are the inflationary cosmology, analysis of cosmological data, mainly Sien-Wheeler crystal structure, reionization, dark energy, study of new physics versus systematics. And today we'll present one spectrum to cure them all. Dhiraj, you can start, please, when you're ready.
Thanks, Eleonora. Am I audible?
Yeah.
Thank you for the kind introduction, and thanks for this opportunity. Okay, let me just make it a full screen. All right. So I'll be talking about a primordial physics candidate as a solution to the anomalies and tensions in cosmology. So that is what the title says, that one spectrum to cure them all. Okay, let me get the laser as well. Okay. Now you all know this standard model of cosmology, but for the sake of completeness, let me go through it once again because I'll be needing this fourth part of it. So we work with in the standard model, we work with Einstein's theory of gravity, and our metric is homogeneous and isotropic at large scales. And for constituents of the universe, we use baryons, cold dark matter, and the dark energy described by the cosmological constant. So nothing more, nothing less. It has a W, or equation state of -1. And these actually constitute the background part of the cosmology. But there is another part which is constrained by CMB the most, which is the initial conditions. For initial condition, we take a primordial power spectrum, which is actually consistent with a complete slow roll inflation. And this is the for standard model, we take it as a power law primordial power spectrum, which can be explained by a complete slow roll inflation and can be explained by two parameters. Actually, we have been able to constrain only two parameters. One is the amplitude and one is the tilt of the spectrum. And so the baseline model, which I will be referring time and again in my talk, is constituted by the lambda CDM model plus the power law form of the primordial power spectrum. Okay. Now, I'm going to talk about two things, anomalies and tensions. So anomalies, mainly I'll be talking about the CMB anomalies. If you look at the CMB spectrum, observed spectrum, you will find that the acoustic peaks in the CMB appear smoother. Okay, so that they are more smeared than the normal or the standard model lensing predictions. And in order to explain that, people work with a parameter called lensing parameter, which they multiply to the CL55, and they get the lensing corrections to the angular power spectrum, TTTE, and then they compare it to the data. So this is not a physical parameter, first of all. This is a consistency check parameter that has been discussed several times in different papers, in blank papers mostly. And what you see is that for standard model, it has to be 1, but it differs from 1 at nearly nearly 2.8 sigma or nearly 3 sigma. And that is mostly driven by the temperature data. TE and EE do not have much say in it because of their large uncertainties. Also, the lensing likelihood doesn't like that. So if you add lensing, it comes closer to 1. So the main anomaly is there in the standard model with respect to the TT data. Okay. Now there is a solution that was proposed discussed in several papers. One of them is Eleonora's paper. As you can see that the closed universe, if you have a spatial curvature, it can solve this problem. It can drag a lens to 1, but it comes with a few other problems as well. I am just going to describe later. So this is what I'm going to refer to as anomalies. And for tensions, I'll be talking about H0 tension, as you know, that the indirect measurements go for lower values of H0, and direct measurements or the low redshift measurements go for higher H0 values. The main two data sets that are in this talk that are discussed over and again are the Planck CMB data and the Rees et al. Data that gets updated and goes, and finds the H0 to be around nearly 74 or so. Now, there is also a tension with large-scale structured data, the S8 tension. Of course, also in the Planck, Sunayev-Zeldovich measurements, there is a tension, but I'm not going to talk about that. The S8 tension that I'm referring to is the tension with dark energy survey or KIDS-like survey, for example, here, the kilodegree survey, where the amplitude parameter, the sigma 8, is inconsistent, is sigma 8 from Planck data, assuming standard model or the baseline is inconsistent with the large-scale structured data of galaxy lensing and galaxy clustering. All right, and that can be summarized in one parameter called S8, which is nothing but sigma 8 square root of omega matter. Okay, now as I said that this closed universe actually provides a solution, but there are several problems that comes with it. Is that if you use a closed universe, the H0 becomes very low. In Planck 18, if you use a omega k model, yes, it changes the acoustic peaks, it does some lensing adjustments, but at the same time, in order to reshift the acoustic peak back in their positions, you need a very low H0. So it becomes inconsistent with all the H0 measurements that we know. And at the same time, it aggravates the sigma 8 tension as well. So omega matter becomes very large. As you can see, the sigma 8 tension with respect to the KIDS papers becomes much more severe. So this cannot be accepted as a solution. And one more very important problem is that omega k makes a problem with the initial condition. If you want to start inflation with a scalar field, let's say, unless you make this, if it is, let's take a canonical scalar field, and if you add the omega k in the background dynamics, it will be very problematic. You will see that you will not be able to start inflation. Even if you start inflation with certain fine tuning and things like that, you will find problems in keeping the modes inside the Hubble radius. So you will be having problem in imposing bunch division initial conditions for all the modes. So the large scale modes, it will have problems. All right. So just one thing, Eleonora, how much time do we have for this talk? According to that, 40 minutes, right? Okay, thank you. So for solution to H0 tensions, there are several papers out there. So I'm sorry if I'm not able to put them in one slide because there are several papers. So I have written a few candidates, but again, this list is far beyond complete. So early dark energy solution is this one, and emergent dark energy solution, which is a late time solution to this problem, scalar tensor theories, early modified gravity, other extension to standard models, systematic in H0 measurements. There are several papers on that. Systematic in the Planck CMB data, there are papers on those as well. However, we try to not go into all this. We try to not touch the background sector of cosmology. We try to see whether the primordial power spectrum sector can be changed in order to answer this problem, in order to find an answer to this problem. All right. So as a common solution, the one main motivation to go to the primordial power spectrum is that the CMB constrains it much better than any other probes, any large scale structure power spectrum probes, etc. And at the same time, it does not have much correlation or strong correlations with the parameters in the background, much strong correlation. So it doesn't, unlike the early dark energy sector where you input one extra parameter, where you add one extra parameter, and that inflates your error bars, right? So here we do not find this problem. So yes, there is one thing is that we will gain some accuracy, but at the same time, we will not be able to completely solve the problem. But let's see how we can, how good we can do. All right. So the approach that we take is that we try to reconstruct, given the data and given the background parameters, we try to reconstruct the primordial power spectrum. So now what will be our recipe is that we try to get a spectrum that mimics lensing. We try to get a spectrum that prefers flat universe while mimicking lensing. At the same time, for those parameters, the spectrum should prefer a higher value of H0 than baseline. And also at the same time, it should prefer a lower value of S8 than the baseline. All right. So let us go back to a few years when Planck 2013 data came. We came up with this paper in 2014. It was the primordial power spectrum from Planck, the name of the paper. We tried to do a reconstruction. So given the data, we reconstructed the power spectrum. So we used the modified Richardson-Lucy algorithm. We developed this algorithm here. It is a modified version of the original Richardson-Lucy algorithm. We iteratively reconstruct the primordial power spectrum from the angular power spectrum. So what you can see that actually, if there are certain outliers, the power spectrum gets peaks and draws in several places at different scales in order to fit those outliers. Of course, many of these, or maybe almost all of these, are noise. So what we do is that we smooth the data. There are lots of error estimation goes in there. So finally, we can find what are the significant outliers, etc. However, while doing that, we learned another thing, is that the reconstruction, a certain type of oscillation can mimic lensing. All right. So this is what we found there as well, that a primordial power spectrum, if convolved with the transfer function, you get the angular power spectrum. Then lensing is added. So if you can only reconstruct the primordial power spectrum, actual primordial power spectrum, using the unlensed data. Now, if you do not unlens the data properly, what happens is that the effect of lensing gets imprinted in your reconstructed power spectrum. So this is the kind of oscillations that you will find if you do not subtract lensing efficiently. So these are the extra oscillations that you will find. So this is the oscillation in the primordial power spectrum that can mimic lensing. As you can see that at certain point of time, if you do the reconstruction with and without considering lensing, at certain point of time, you will find certain oscillation in the primordial power spectrum that can give a very close chi-square. Okay, this is the log likelihood minus log likelihood. If you consider lensing, or if you do not consider lensing but consider this type of primordial power spectrum. So as you can see that the mimicking effect is also seen here. Okay, so this is the lensing template corresponding to the total lensing template corresponding to a lens equal to 1. This is not just the extra part corresponding to the excess lensing that we are finding. We also tried another thing. We tried to ask the question that, okay, this is the standard baseline best fit primordial best fit angular power spectrum. Now let us say I want to have a higher H0 and lower S8. Okay, so we took the parameters. We went to a parameter space where we have a higher H0 and tried to reconstruct the primordial power spectrum. So this is the spectrum that we had obtained. So if you use this spectrum, your H0 value will shift to 73. Your omega matter will come down to 0.26. And at the same time, we found that, okay, if we do that, it solves the S8 tension as well. So Planck plus reconstruction lies here. At that time, this was the state of the tension when this was the state of the tension. But the thing is that this becomes a very complex primordial power spectrum. So what we commented that this looks similar to this one, but in order to get it from an inflationary physics, it is very hard. We will not be able to do that. Okay, so we said that it is nearly impossible. There was another paper by Zhiqi Wang who actually used the reconstruction, and he said that he inferred in his paper that it is not possible to increase H0 using a primordial power spectrum, using different shape of the primordial power spectrum. However, that statement is not completely correct. It is partially correct. Most of the cases, a feature in the primordial power spectrum drags H0 to a lower value instead of going to a higher value. And but the thing is that in earlier efforts like this and by Zichi Wang's paper, we failed to see the actual picture. Then after this, Planck 2018 paper came with a version 2, with the second version. It was not there in the first version, that actually proposed a solution to the aliens problem, which is similar to our reconstruction. Okay, so this sinusoidal oscillations that you are seeing, they peak at 0.1. So Planck proposed this, and you fixing all the parameters except the amplitude parameter ALIN and the aliens. They ran this thing against the Planck data and found that aliens problem is solved with this type of primordial Gauss spectrum. Okay, so you see that there was already some certain efforts that were going along the line. All right. Just a second, let me get the track of the time. Okay. Okay, now we come to one spectrum, all right? So as we said that we wanted a spectrum that mimics lensing in a flat universe with higher H0 and lower sigma E. So in order to obtain the one spectrum, we had the idea that let us not try to fit the full lensing with the primordial Gauss spectrum, but just try to mimic the excess lensing effect. We say that let us assume the excess lensing effect is actually a primordial signal. Treat the best fit baseline aliens best fit to the Planck TT data as the input spectrum for the reconstruction. We think that is a data, okay, the smooth data. So if you just use the data, then you get oscillations like this. But now we are saying that, let us say that the aliens plus TT, alien baseline plus aliens best fit to Planck TT data is my data, and we use that for reconstruction. As I said, for the reconstruction, we need an unlensed data, okay, unlensed CMB data. So we subtract the lensing effect corresponding to A lens equal to 1. It is very easy to get that. You just go to the CAM, use the all the parameters of this baseline plus A lens, but put A lens equal to 1. And then you subtract these two the scalar CLs with respect to the lens CLs, and you get the lensing effect mainly. So you will get a template like this dotted curve, and then you subtract. So that is now your unlensed data, let's say. So what is remaining there is that the residual excess smoothing corresponding to the 10% excess lensing. All right. And if we do the reconstruction now, it is expected to capture the primordial features that can mimic the effect. So what we get is this. As you can see that this has much less oscillations or much weird oscillations like this. At the same time, the amplitudes is much lower compared to what we got for the full lensing mimicking trial. That is because of the fact that we are not trying to mimic the full lensing, only the excess part. Okay, because we know that lensing is there. Lensing is a physical artifact. Okay. Now, at the same time, you can see that it has a pattern, and we can actually get an analytical fitting function to that. So, but before going to the analytical fitting function, we tried this spectrum, okay, with just an amplitude and a horizontal shift in this of the position of the oscillation, and try to fit it with the Planck data with the addition of different components. First, we tried the A lens, okay. So it is our reconstruction A lens that brings down the A lens value to nearly 1. You see that it is completely consistent with 1 if you use this spectrum instead of the gray one. And if you use the gray one, you will get this red. Now, we want to see whether the chi-square is similar or not. So we get the chi-square distribution function of the chi-square CMB. So this is the reconstruction. This is the standard model plus A lens. So we see that the distribution of the chi-square is very close. It is actually mimicking. So reconstruction plus A lens is here, reconstruction is here. So this is actually mimicking the full A lens effect. Okay, the distribution of chi-square is also the same. Now, instead of A lens, now we add this omega k in that spectrum. What we find is that the omega k becomes closer to 0. Actually, it becomes consistent with 0 at 1 sigma. So it prefers a flat universe. It also mimics, of course, you have seen Eleonora's paper, as I mentioned, that the omega k mimics the aliens in the angular pause spectrum. So it is not surprising that a reconstruction, the distribution of the chi-square CMB is going to mimic the standard model plus omega k. Okay. And if you just use the standard model, you see that chi-square is higher, okay, nearly 10 higher than the extended models. Now, how does it brings back the cosmic concordance? So this is the plot of omega k versus lns. So now we just plot the same thing with the reconstructed primordial pause spectrum. So this is the standard model. Of course, this and this has a difference. This is using TT only, Planck temperature only. And this becomes the lns equal to 1 and omega k equal to 0 lies at the edge of 1 sigma of this 2D contour. Okay. So this is what we find, that if you use this spectrum, you get this. Now, the thing is that at the same time, if we ask the question, as I said, that whether the spectrum is a good fit to Planck data, yes, because you are seeing that the chi-square decreases. Okay, it decreases to 10. It decreases by 10. Sorry. Yeah. Now, let us see what happens to H0. We find that with the increase in likelihood, with the decrease of chi-square, it is actually preferring, our reconstruction is actually preferring a higher H0. All right. So whether you take omega k or whether you just work with the just use the reconstruction. So this is the standard model. If you use standard model, means mainly I'm referring to the primordial pause spectrum as power law part. If you use one spectrum, then you get a shifted posterior of H0, shifted to the right direction. Okay. And if you use omega k, as you have seen, that the omega k value goes below, if in the standard model, below 50, but in our case, actually it shifts to the right hand side. So the oscillations we obtained actually prefers a higher value of omega k. That means, and it is closer to 0. So it prefers a flat universe. S8 problem. So this is what we find, that this was the kids 450 results. This is reconstruction plus omega k. Okay, this is standard model plus omega k, the red one. You had seen the discordance. But if you use the reconstruction, our primordial pause spectrum, then you will see that it actually drags it towards the S8, towards the S8 that is obtained by kids 450. All right. It also prefers a lower omega matter as well at the same time. And the S8 value, okay, so this was the sigmoid versus omega m. The S8 value shifts towards a lower, lower direction, right? So this is the kids 1000 result. So we just plotted the band, and we can see that in both the cases, if you use omega k, it basically shifts it to the left direction. All right, which is the preferred direction. Okay, another thing which is not a tension actually, but what we found that actually it is also trying to go to the preferred direction, that globular cluster measurements, there are a few papers by Vasin et al. Which are referenced in this paper, and which shows that the standard model doesn't have a 1 sigma overlap with the age of the universe obtained by globular clusters. So they show this bands in this age versus H0. And what we see that if you use our reconstruction, it comes to the preferred direction. It decreases the age of the universe to a certain extent. All right, but we are not saying that it is since it is not a big tension. Let us not talk about that more. All right. So what we find from one spectrum is that this is a spectrum that mimics lensing. This spectrum that prefers flat universe while mimicking lensing. And it prefers higher H0 than baseline. Of course, it is not solving the problem, but it prefers, at the same time, it prefers lower S8 than baseline. So why this is important is that almost all the models that have been proposed, modified gravity or early dark energy and few more in this as an attempt to solve this problem of H0. We have seen that the S8 increases. So in order to solve one problem, you are actually aggravating another problem. All right. At the same time, it does not have, those solutions do not have any say about the lensing part. Okay. So if the blank lensing anomaly is a true anomaly, so that those solutions cannot be treated as a common solution. So this is why we think that this one spectrum is important. Moreover, it actually can be obtained from inflationary models. I'm going to talk about that. Now, next question is that, okay, spectrum, you have now fit it with the data. Can we assess the significance of these models with respect to the data, with respect to the standard model against the data? For that, you need to parameterize these models. And we have found that parameterization is possible. So this is the power law standard model. We modify this with a sinusoidal oscillation and a damping factor 1 plus beta. Okay. While at that time, we also later on, when we finish this work, we'll realize that at a certain point of time, it actually merges with also the Planck's suggestion of this primordial power spectrum, which was the sinusoidal oscillation, which we obtained also in our reconstruction here. All right. So around that time, we found that this spectrum with these free parameters, alpha 1, omega, alpha 2, k naught, and beta. So there are 5 parameters, can mimic this primordial power spectrum, reconstructed primordial power spectrum. We tried to fit this data, but we call it a new spectrum. But we found that this alpha 2 parameter, this has only 1 sigma significance. 1 sigma significance is not very good. So we tried to see whether we can get reasonable fit to the data without that. So we dropped that, and the primordial power spectrum became simpler than what we wrote here. Okay. So this is what we have now. It has 4 free parameters: the amplitude, the frequency, the k naught, the position of the peak of the peak of the oscillations. There is a peak in the oscillation because there is a decaying factor, so which decays this oscillation around that value, k naught value. So we fit this data. All right. We find that the log p, the difference of this, the ratio of the base factor, if you use just TT data, it is not preferring our model. All right. If you use restricted spectrum with 4 parameters, it is as good as the standard model. Though it provides an improvement in fit on nearly 10 or so, it does not in the Bayesian scale. If we have obtained it with CosmoVerse, in the Bayesian scale, it is not preferred, right? Just have time. But if you use HST, Planck TT plus HST, okay, so I'm going to also say why we had used HST. There are talks that, okay, we should not use 2 competing data in combination to constrain a model. I'm coming to that. But what we find is that if you use HST, we get significant improvement, and we get evidence for our model, the restricted spectrum. It becomes 3.4. All right. In order to see the correlations between the parameters, we have one amplitude parameter, right? The amplitude of the oscillations. So we just try to see whether the amplitude, how the parameters are correlated. So if you increase the amplitude, all right, you see that A lens decreases. So it is negatively correlated. If you increase the parameter alpha 1, the amplitude, the omega k increases, it is positively correlated. We have seen this thing in our reconstructed spectrum itself, but this is from the amplitude perspective where we have parameterized it. Okay, now if it is negatively correlated with omega matter, so it gives rise to lower matter density. It is negatively correlated with S8, and this is positively correlated with H0. So this is actually what we want. So this slide is very important. So we have the changes in the preferred direction. All right, all the changes in the preferred direction. We tried to use different data sets combinations, and these are the best fits that we have obtained. We just plotted the best fit. One important thing that you can see is that in order to solve this problem, the NS increases if you use TT, but again, if you use TP and all the other data set, NS again decreases. The spectral tilt. So spectral tilt, if you increase the spectral tilt nearly 0.98 or something like that, you see that alongside these oscillations, of course, you see that your aliens becomes closer to 0. Okay, you can also see that in Planck paper where they just plot for the standard model the correlation between NS and aliens. And this is the full table of our analysis. If you use temperature plus polarization only, you do find that it is not preferred. It is just as good as the standard model. If you use HST, in all the cases, if you use HST, you find that the confidence level and the same time the base log of the base factor increases. Okay. In certain cases also, we have found that yeah, we do not find significant, we do not find increase in the base factor because we are not able to constrain all the parameters, but the significance of this alpha, the amplitude parameter, alpha 1, that becomes closer to 99%. All right. So we should not trust this number after the decimal places too much. So we can say that it is of the order of 99%. In order to get even better result, you have to run the Monte Carlo with the lower temperatures, etc. But anyway, now, does it have any implications for the large scale structure? The K naught, all right, the scale, sorry, the omega, the oscillation frequency, that actually says that at what radial scale in megaparsec, there will be changes in the correlation function. So we see that there is a significant change in the correlation function around this scale. So this is, we are plotting the correlation function with respect to the radial distance in megaparsec. So around 300 megaparsec, you can expect a change in the large scale structure. And this is the P of K and the difference of the P of K with respect to the standard model. Now, I told you about the reconstruction. So this is the work, these two, the first one I already showed you, this one, Hazra Anthony Safilu 2022, came around, I think, January or February, and this is just 1 month later. And this one actually attempts or provides a solution, not just attempt, it provides a solution to this primordial power spectrum. In the first work, it is a top-down approach. You see that we try to get the primordial power spectrum from the data in a model-independent way. And the second one is the bottom-up approach, that from the inflationary theory, can we fit the data? Can we get to the power spectrum? Okay, so in both the cases, I mean, in both the approaches are important. This is what I actually say in most of my talks, that in order to understand the physics, you need to combine these two approaches, the bottom-up and the top-down. So what we find is that if you have an intermediate fast roll phase in the scalar field dynamics, you can provide an explanation of this primordial power spectrum. Now, we parameterize it in the Hubble flow function. This is the epsilon h, okay? And the epsilon h is, you know, minus h dot by h square. And the baseline, we use a baseline. I'm going to describe the baseline right now. And this is the modification to the baseline that you want. Very simple. It is very close to that, but usually it is not simple. Okay, it is not one-to-one that if there is a sinusoidal behavior, you will get a sinusoidal behavior or something like that. It happens the opposite. If it is a sine in the in your potential, you get a sine log or the resonant oscillations in the primordial power spectrum. If there is a kink, you get a sinusoidal oscillations in the primordial power spectrum, but with a completely different profile. But if you combine these two magically, or I mean, of course, it happens physically, but magically, I would say, because it is mimicking completely the power spectrum that we obtained, this one, that it has the ability, how it can do that? It has the ability to get the sine log resonant and also the sharp oscillation and their combination. So that actually gives us a wide prior range where we can explore the parameter space and get the best way. What is the baseline? Baseline is something that should allow a wider variation in NS and R and the AS. Okay. AS is simple. Now, let me tell you for 1 minute why we have chosen to work with the Hubble flow functions, the slow roll parameters. Okay. The reason is that, let us say we use a m² phi² model. In m² phi² model, NS is 0.96, but we need a variation in NS. You need a different model, or you can change the n star there. Okay, when the modes of pivot scale leave the Hubble radius, but you can make it 50 to 60, but NS doesn't change much. So in order to get a different NS, you either have to change the potential or the n star, which can be degenerate. So there can be several effects. So it is not possible to marginalize over all the potential in a single potential framework, right? So therefore, we tried to work with this, and we found that this one parameterization allows us to marginalize over all minimal slow roll potentials. And we're not using any slow roll approximations. Given this, we are solving the background equation and the Mukhanov-Sasaki equation. Now, why I said that this is sufficient to marginalize over the all slow roll models? So because NS can be given by these two parameters, 1 minus twice epsilon1 and epsilon2 minus epsilon2. R can be given as 16 epsilon1. The spectral amplitude is proportional to hi square by epsilon1. Hi is the initial condition of the Hubble parameter. So when you solve the differential equation, you just provide this one as the initial condition. So this one acts as AS, similar to AS. This one acts as a R, your tensor to scalar ratio. This combination acts as your NS. All right. Now we do not have to rely on any primordial power spectrum, any power law primordial power spectrum. We can work in the space of inflationary physics. We do not have to use the primordial power spectrum as. Okay. Okay. I think I am. Okay. I think I'll be finishing in 5 minutes. Okay, now, as I said, we solved the Hubble flow function numerically to obtain the evolution of Hubble radius during inflation. And we also use Barnes-Davies vacuum initial condition. Then we solve the full Mukhanov-Sasaki equation, both scalars and tensors, to get the primordial spectrum. Okay. Again, note that there no assumption on the potential goes in here. Okay. And we work with the canonical Lagrangian. We work with these data sets, Planck temperature plus BK18. Without temperature, we use the polarization and the cross correlation. And S21 is the Sues et al. 21 results. TP is the temperature plus polarization, TTTE, low T plus low E. And this we also work with S21, and temperature polarization plus lensing is denoted as TPL. Now, for 1 minute, let me just explain why we are using Sues 21 data. Now, when two data sets are in tension, we have heard this argument that a model, with respect to a model, an analysis combining the data sets will provide an unrealistic posterior on the parameters, because there will be drags. Okay, in such a case, the drag on the parameters from both data degrades the fit to both data sets, and the posterior will become divided into two parts, not always, but it will be centering in the middle region. Okay, of these two observations. Now, on the other hand, compared to the baseline parameterization without using S21, the Sues et al., we find that the posterior of H0 shifts to a higher value. There is a 1 sigma shift, not much, but we have seen that it shifts. Definitely, this is also an effect of the parameterization. There can be a better parameterization to the one spectrum that can give rise to even 2 sigma shift, because we have seen that even without the S21 or any HST prior, one spectrum shifts the H0, okay, to nearly 71 or so. We get nearly 8 to 11 improvement in chi-square. When Sues et al. 21 is used, SUS21 is used, sorry, not SUS at all, SUS21 is used, we find that the best fit to the joint data provides nearly 20 improvement in fit. Now we see that what is the fit to the fit to the CMB data. We get the chi-square CMB data in the joint fit, and then we compared it just with the standard model best fit to the CMB data. We found that it is nearly 3 chi-square better than the baseline best fit to the CMB only data. Okay, so we get 70 H not equal to 70, but at the same time we get nearly 3 chi-square better than the power law fit to the CMB data. This is the table. I'm not going to discuss this much, but you can see that without using the H0 HST prior, you can see that H0 increases. This is 66.86. This becomes 68.06. S8 also decreases from 0.84. It becomes 0.81. So this is important. At the same time, NS increases 0.963 to 0.971. Omega matter decreases. Doesn't happen so for TTEE or TPL. TPL means if you use lensing, it degrades the fit. We are getting nearly 11 fit to the better fit to the TP data, temperature plus polarization data with bicep and GEC data. If you use SUS et al. Data, then you start improving the fit even more. You get nearly 20 improvement in fit to the data. These are the best fit spectra for different analysis. I'm not going to discuss this much. I can come back to it if there are questions. Now, of course, there is this degeneracy that lensing anomaly is given, the delta DLTT is given like this. There is a degeneracy, as you can see, at the small scale. The model of inflation is actually mimicking this. But they are out of phase. These oscillations are out of phase if you just look at the EE data sets. Okay, so in the polarization, it is out of phase. If you use a CMB S4 like survey, as you can see, this is the error bar. This is going to be the error band. So you will be able to distinguish between these two observations. Another important thing is that we have seen that if you do not use Planck polarization data, but use ACT polarization data, we get more favorable answer to our solution. Okay, more favor to our solution. Okay, so we get better better base factor to our solution. Now we did not use any potential, but you can reverse engineer the potential using this formula. This has been discussed in Planck papers as well, and many other papers. You can simply get it from the scalar field equations. And the reconstructed potential, the modified potential, you can take any baseline potential, m square, phi square, or anything. You can get these oscillations by using this type of modifications. The modifications look very similar. Fractional change in the slow roll function, it looks like this. Note that the change is between 17.8 folds to 18.3 folds. Of course, I mean, this is you can shift the number. This number is not important. N star is important. So what you can see that you need a change nearly for 0.5 E folds, all right, in the slow roll. So you need a fast roll or breaking of slow roll of about 4% to 6% for only 0.5 E fold of inflation. This is the second slow roll parameter, fractional change in the second slow roll parameter. This is the Hubble parameter, the change that you need. And this is the change in the potential that you need. So we find strong support for an intermediate fast roll for 0.5 E fold of inflation. So let me just summarize and provide an outlook in the last two slides. So we showed in that correlation plot that anomalies and tensions within and between cosmological observations are correlated. So if one goes in one direction, the other goes in the other direction. So there you can find, so there exists a common solution that can answer this correlation, that can positively resolve these anomalies and reduce these tensions. Then one spectrum is a solution. Okay, this provides a common solution. We find statistically significant preference for an intermediate fast roll for nearly 0.5 E folds, as I just said. And this candidate has a strong signature in the CMB polarization and large scale structures at particular scales that can be tested soon with upcoming data. But word of caution is that it does not solve all the tensions in cosmology. H naught, we do not solve it completely, but again, we know that it shifts to the right direction. As I said, it seems it is the only solution till now where the shifts in the parameters are in the directions to resolve the tensions. They are all in the preferred direction that we have seen. The solution has a physical origin. You can get it from a model of inflation. All right. You can also, when I say physical, I'm not talking about we have found a high energy physics candidate for that, but we have found a phenomenological model. We have a potential that can solve this. Lensing likelihood, and if you add BAO and supernova measurements, they decrease the significance of our solution because these actually likes a higher value of omega matter. Again, you should not use all the data together, but the thing is that we have to see in future what happens. And given the origin, other correlation can also be compared with the data, such as bispectrum. We are working on that. So with that, I would like to stop. I'm sorry that I have gone over the time limit. So I'll take questions.
Thank you so much. Thank you.
Thank you.
Okay. So any questions?
Yeah, I have a question. Hi.
Hi.
Thank you for the talk. I'm sorry, I just joined a little later
No
because
problem.
my previous meeting didn't end soon enough. I was going to ask, so you were anchoring using the Hubble flow instead of the parameter descriptions in order to be a little bit more model independent. Yes, over there. And I was only wanting to note that even if you use the Hubble flow, that n star you have here on the E folds, what we call the pivot scale, still needs to be sought. So when you're doing parameter exploration, exploring the parameter space, you still need to look for the optimal pivot scale in K in order to get the best constraints on NS and R, particularly here because you're using the running as well, right?
No, here is no running. Here is no running actually. So if you use that, all the higher orders than the tilt are not there. So you just have, if you solve this, you will see that you will just get an amplitude and a tilt. That's it. There is no running in it. So in star, what we are talking about is something just we fix it to 50. That means that if we say that inflation ends at 70, it means that from the beginning, the private scale, beginning of inflation, pivot scale leaves the Hubble radius around 20 folds from the beginning of inflation. So if you change in star, the constraints on epsilon 1 and epsilon 2 will change similarly, but we have seen that there is a complete degeneracy. So there is no point in putting in star as a free parameter.
Exactly. Yes. Yes. So this is just in the case of the NS not being constant with cosmological scale K or inverse scale K. Then you have a preferred scale for looking at parameter space. The second question was about which parameters set to choose to alleviate the tension. If you use shoes, knowing that all CMB parameters are very degenerate with H naught, aren't you putting in the answer at the same time as you're getting the solution?
Okay, we are actually varying all the parameters here. Means that we are varying all the all the potential Hubble flow function parameters, except one where we have also seen that it is actually completely the beta. We found that we just have a lower limit on beta. So we just fixed that and it is completely degenerate. You can use, you can trade off between parameters. So there are 3 extra parameters. We are varying that but we are also varying this 3 parameters for the baseline models, that HI, epsilon 1 and epsilon 2. We are varying these 3 parameters, and all the background parameters we are varying, means that omega baryon square, etc., plus the plus all the nuisance parameters. So, and the prior range is really, conservative. So it is not that the solution. Okay, I should say that. Okay, is your question saying that is on for what parameter we are able to resolve this tension? Is it, or should we fix this parameter? Okay, no, you should not. First of all, yeah, please.
It's just obtaining constraints on inflationary parameters that we all know are very degenerate with the value of H naught chosen. And then knowing that there is the tension and using one parameter set, which is shoes, shouldn't we use both sides of the answers for H naught, or marginalizing over them to get constraints on inflation?
Oh, okay. So no, this HI and that H naught that we are seeing here are actually disconnected, because this HI is something that, of course, they are, I mean, they are physically connected, but when we are talking about H of during inflation, we're talking about a scale that is of the potential scale. But then in order to, but then there are reheating and several factors that are coming in. So that we are neglecting. So this does not have any correlation with the H naught as such. In the parameter space degeneracy, you might find some correlation because of the change of scales, etc. But this is completely data-driven correlations. Yeah.
Thank you.
Thank you.
Okay, thank you. Shaheen, you have a question?
Thank you for the nice presentation. Actually, I have two questions. One is that probably we can mimic the spectrum that you mentioned and the correction to the spectrum through non-Bunch Davis initial states. And we need not actually change the potential. We have done this in a couple of papers back in maybe about 10 years ago. So changing the potential is not the only way. And maybe it's even more physically interesting to play with the initial state of inflation. So this was one comment. And you mentioned also including supernova and BAO data in the last slide. Would you elaborate on this?
Okay, so whenever you use, okay, I'm coming to the second point later. This one is, when we use this BAO plus supernova measurements in that, in this plot, in this table, you see that every data has a preference of their own parameters for their own parameters. Sometimes they are in tension with other data sets, but sometimes they are not, they're consistent. Now, when we have seen that BAO and SN, whenever you use them, they are actually preferring a higher value of omega matter, which is nearly 0.32 or something like that. And in order to solve this S8 and H naught and all these tensions, you will see that this A-lens will be negatively, or A-lens, if A-lens, in order to decrease the A-lens, you will see that your omega matter has to decrease. Okay, so that is something that is there, or NS has to increase. So these things are there. NS is not coming here because it is a background measurement. In BAO, it comes to a certain extent, but we are also using the geometrical measurements, right? But here, mainly what happens is that omega matter increases. In order to support that omega matter, NS cannot increase in the CMB. So if in the CMB, NS and omega matter are correlated in such a way that in order to increase omega matter, your NS has to, if omega matter increases, NS has to decrease. That is the degeneracy in the CMB. Since we are using all the data set together, so if one particular data set has a preference towards a particular parameter like omega matter, it actually messes up with other parameters because of the residual degeneracies that are there in the CMB. Okay.
Yes, but actually the question was, why shouldn't we combine or consider supernova and BAO?
No, I'm not saying that we should not combine. I'm just saying that this is these are the actually that we are not able to solve. These are the two negative points in our model that we solution. lensing likelihood and BAO-SN measurements are not in favor of our model. They decrease the significance. If I have answered this one, let me go back to the first question. The bunch Davis one that you said, it gives the sinusoidal oscillations as well at the and it is in transient and at these scales.
Yes, you can actually find some initial state which does this.
Yes, but if you are using a non-bunch Davis vacuum, then all the modes that will be leaving the Hubble radius will be affected, no?
It depends on the initial state that you choose.
Okay, so I will have a look at your paper because I have not seen, because I knew that it actually gives a persistent oscillations at all scales if you use some excited states, etc. in the as a non-bunch Davis vacuum. But another thing is that I have not worked with non-bunch Davis vacuum in the sense that in a canonical scalar field or even non-canonical scalar field, the direct solution that you get is the bunch Davis. The simplest solution that you get is the bunch Davis when you say that K is very greater than H.
That's one usual convenient choice, but that's not the only one.
Okay, so if it works, I will be happy to know more. Yes,
sure. I'll send you an email and
please
with the reference. Sure,
please.
Thanks.
I would like to remind you that we have a Slack channel where we can continue the discussion.
Okay, sure.
Also, if you want to share materials, okay, we're happy about that. Okay, thank you. Now, Leandros, you have a question?
Yes, thank you for the nice talk.
Thank you.
I think the idea is quite interesting. I'd like to ask a couple of questions. The first is about the parameterization you used. You've used. Have you tried different parameterizations, or how did you end up with this particular one? Which
yeah, okay, we are trying a couple more. So this is something that we have tried. Now we have shifted our attention to some other implications of this using this parameterization, but we have one or two parameterization in mind as well. What we found is that this power does not matter. So it can be 4, etc., 4, 6, whatever you want, any even power is going to work. And whether it should be a log space oscillation is something that we will be trying as well. We have not yet fit the data using those parameterization.
Okay. And another question, can you show again the fit to the for the H naught and the S8, the probability distribution functions?
Yep.
For the reconstructed
Yes.
Yes, here. I see that the reconstruction model has a significantly smaller uncertainty than all other models, while one would expect to have larger because you put in more. This is a more general model. Why is this
yes.
smaller uncertainty?
Exactly. So what happens is that in the reconstruction model, that is why we went to parameterization. Here, the oscillations are of this form. What we are doing is that we are basically shifting this up and down the amplitude, but we are not allowing the NS to vary. Okay, because that we kept it for the later phase when we are actually parameterizing this. We are just trying to see that if this is the oscillation pattern, to what extent the H naught changes. That is why, because of the non-variation of NS, it is a very nice spot. This is very nicely spotted that in all the cases, you will see that the contours are smaller. Here also, you'll see that the contours are smaller. That is because of the non-variation of NS. So it basically, but this was also important that this is the best fit. If this is the best fit, then that best fit wants an H naught like this. What it says, for example, if you look at the gray contour, the standard model, it means that if you want to have an H naught of 71, the chi-square should increase drastically. The likelihood decreases drastically, right? But here we are actually 71 is the best fit. So the thing is that this is our start. This was our starting point. Now it comes to the parameterization. If we are able to parameterize it even with 2 parameters or something like that, then it will be really good that it should not even, I mean, the 1 sigma shift that we are talking about, that can be 2 sigma as well. So yes, then after that we added parameterization, which you will see that increases the uncertainties that you can see here as well. So here the H naught from P18TT is the error bar is 0.86, but in our model it is 1.14. This is the baseline result, but this is in our model it has increased.
I see. Okay, thank you.
Thank you.
Okay, I have also a question. Okay, because
Please.
my understanding is that that this model was suggested by the fact that there is an excess of lensing in Planck. So we're trying to solve this A lens problem, and then you found that you can increase H0 and decrease S8. So what happens with the alternative CMB ground-based telescope that don't have the A lens problem? So is this something that we can still see? So this improvement in H0 and S8?
Yes. So what happens is that so this is something that we had commented in our paper, that if you just use ACT, we find that the best fit frequency is the same. Okay, but it has all the oscillations all the way, because ACT doesn't have a large or intermediate scale measurement, right? So we see that the small scale oscillations are there at the same frequency and at the same place. So, but in the combination, when we see this combination, for example, P18TT, we see that these are also consistent, and at the same time, it increases H0. But if you, for example, P18TP ACT plus DAS, there is no HST measurements, HST prior has been used. We have seen that H0 increases. Now, we have not used ACT just, when we, as I said, when we use ACT without any Planck thing, then we see that the oscillations are there, but H0 does not change much like Planck. Since Planck has a better error bar, it actually gives more weightage to that spectrum as well compared to ACT. One observation, as I said, that if you do not use Planck polarization but use ACT polarization, you will find a improvement, a little marginal improvement in fit in the base factor. So if you see that this is 1.94, here it is Planck TT plus ACT, it is 2.28. So it is a little bit better than Planck polarization. Now, I think we just have to wait till a cosmic variance limited polarization comes in, where we can answer this. So yes, so this is some. Yeah,
okay, thank you.
It is. Thanks.
Do you have any other questions? No? So, okay, let's thank Dhiraj again. Thank you so much.
Thank you. Thank you, Eleanor, and thank you all for listening to my talk. Thank you.
I stop the recording.